Hi, Physics 1, Mr. Janowski here. This is part 5 of the Chapter 10 slides. So in the last part, we learned about inertial and non-inertial frames of reference with those wonderful drawings of Billy skating in the truck that I made in Google Drawings. They took a long time. I hope you appreciated those. So we'll keep going and we'll learn about different frames of reference and a weird one that's kind of a staple in sci-fi movies. So hopefully you find it interesting. So let's get started. Well, one thing is normally at this point in the year, we would have taken a break from the slides and gone and done a lab, and it's a wonderful lab and people enjoy it and it's a lot of fun. So hopefully we'll get to do it this year. It's not impossible that we'll be back this year in person. And if we are, I really hope we have time to squeeze this in, but we'll see. So yeah, no lab for you guys at this point, but keep your fingers crossed. So, do now questions. What is an inertial frame of reference and why do we like them so much? An inertial frame of reference is a frame of reference that is not accelerating. So, yeah, the words are weird. It is inertial, that means it is not accelerating. If it is non-inertial, that means it is accelerating. But anyhow, inertial frame of reference is a frame of reference that is not accelerating. We like them so much because Newton's laws and all of the other physics we've learned so far this year work perfectly well as long as you're in an inertial frame of reference and you're making all of your measurements in an inertial frame of reference. So all the kinematics, all the F equals ma, conservation of momentum, conservation of energy, all of that stuff works perfectly well as long as you're dealing with inertial frames of reference. If you're dealing with non-inertial frames and you're making your measurements in those non-inertial frames, then things get weird. So yeah, we really like the inertial frames of reference. So can an object have a constant speed and be accelerating at the same time? The answer is yes, because speed is not the same thing as velocity. Speed is only the magnitude of velocity. Speed is the scalar version. Speed only has magnitude, velocity has magnitude and direction. So if your object has a constant speed, the magnitude stays the same, but if it's changing directions, such as if it's going around a curved path, then it is accelerating because a change in either magnitude or direction counts as acceleration. So ask yourself, are these frames of reference inertial or not inertial? So the first case, we have a car driving with a constant speed in a straight line. Is that inertial or non-inertial? Well, you have to ask yourself this question to figure that out. Is it accelerating? This is the question that gets at the heart of this idea. So a car going at a constant speed in a straight line. Well, it's got a constant speed, so the magnitude of the velocity is not changing, and it's going in a straight line, so the direction of the velocity is not changing. Therefore, the velocity is not changing, so it is not accelerating, so it is inertial. So yeah, not accelerating means inertial frame of reference. This is the good kind. How about if you have a car driving with a constant speed going around a circular track? Well, ask yourself the same question. Is it accelerating? It has a constant speed, so the magnitude of the velocity is not changing, but it's going around a circular track, so the direction is constantly changing. Changing in direction counts as acceleration. That's not the way we first think of acceleration, but it's perfectly legitimate. If you're changing either magnitude or direction or both, then you are accelerating. So if you are accelerating, you're in a non-inertial frame of reference. And every year people like to flip these, the definition of the term, and yeah, they flip which one's which, because it does seem kind of backwards. If you are not accelerating, you are inertial. If you are accelerating, you are not inertial. So yeah, commit those to memory, however your memory works. Another thing to point out, velocity does not equal angular velocity, and acceleration does not equal angular acceleration. These guys are cousins, but they're not the same thing. So when you're trying to figure out this inertial and non-inertial thing, you want to look at the velocity and see if the velocity is changing. You don't look at the angular velocity, because if that's not what does this thing. If your velocity is changing, your regular old-fashioned v velocity, if it is changing either in its magnitude or its direction, or both its magnitude and direction, then you are accelerating, and therefore you are not inertial. Don't look at omega, don't look at alpha, look at v, because if v is changing, then you have acceleration and you are non-inertial. People like to mix this up too. So in their non-inertial frames of reference, so we saw this picture last time up top. This is called a zero gravity ride, a terrible name for it. In the non-inertial frame of reference, these riders, especially this guy in the yellow, who's the most easy one to point out, they feel this fictitious force, centrifugal force, that's pushing them against the wall. If you're watching this from the ground, you know that there really is no such thing as that fictitious force. It's just that this guy in the yellow shirt is trying to do his physics in a non-inertial frame of reference. So he feels he has to invent this fictitious force called the centrifugal force to explain what's happening. So in this picture down below, astronauts in a spinning space station, they can get a sense of artificial gravity. I say that we haven't actually built one of these yet. These are all over sci-fi movies. You have the spinning space station, and that's how they make the gravity. And we're going to look at that. It would actually work, with the caveat that we'll get to. But yeah, it would actually work. So this particular gift down here is from a very famous, very important movie that I love. So do you happen to know what movie this is from? 3, 2, 1. It is from 2001, A Space Odyssey. Stanley Kubrick. Wonderful movie. I love it tremendously. A lot of people your age think that it is slow. It is rather deliberate, but it's wonderful filmmaking. Its cinema has an art form. It's incredible. Yeah, I love this movie. You should watch this movie. You've got time right now. Watch this movie, 2001: A Space Odyssey. So it's kind of hard to see how this would actually do this. See, I would normally in class I would draw a nice picture on the board that would kind of explain what's going on. I don't have the picture here. So yeah, if you were in this spinning space station, you were the astronaut in the spinning thing. If the astronaut were to hop up in place, he would say that gravity is pulling him down to the floor, artificial gravity. We would see it differently. We say that, well, there's no actual forces on this guy as he's spinning around. As this thing is moving, he's spinning around. He's got straight line velocity. He's got, tangential velocity. And he has that the instant he leaves the floor. So when he pushes off the floor, he's going to hop up in the air. So he would hop vertically in that weird frame of reference. But he still has his tangential velocity, which would bring him to the side. So he would go in kind of a straight line to the side. And we would say that the floor actually accelerates up towards him. I know this sounds very complicated when you do it in words. Normally in class, again, I would draw this on the board and talk you through it step by step. But yeah, he's saying in his non-inertial frame of reference, his accelerating frame of reference, he says there's artificial gravity pulling him down. We, in our inertial frame of reference, say that's not exactly what's happening. If this guy here, his name is Frank, as it turns out, if he hops up in the air, it's actually the floor that accelerates up towards him as he moves sideways with his tangential velocity. It's confusing. So, the artificial gravity section of the USS Discovery 1, which was the name of the spaceship in 2001: A Space Odyssey, it has a radius of 6 meters from the axis to the floor. So, from this part here over to the floor in any direction, this is a circular part, that radius is 6 meters. I'm guessing that Frank's height is about 2 meters. So, a couple of questions. With what angular velocity must HAL is the computer that controls everything on the spaceship, and I don't want to ruin it for you. HAL is a wonderful character. With what angular velocity must this computer rotate the spaceship in order to create, there's a typo, an artificial gravity equal to that of Earth at Frank's feet? And then if it rotates the spaceship at that angular velocity, with what will the artificial gravity at Frank's head be? Because his head is 2 feet closer to the axis than his feet are. So first part, with what angular velocity must HAL rotate Discovery 1? So what are we looking for here? We are looking for angular velocity is omega, and it will be in units of radians per second. So how do we do this? We say we want the centripetal acceleration at Frank's feet to be equal to the sense of gravity. I'm sorry, to be equal to the gravity on Earth. So we've got this, a sub c, centripetal acceleration. It's equal to v tangential squared over r, but this time it's going to be easier to use the other formula, r omega squared. So r omega squared, the centripetal acceleration at his feet, is equal to the feeling of gravity he feels at his feet. So solve this for omega. Turns out omega is going to be equal to the square root of g at his feet divided by the radius at his feet. So you plug in the numbers, you get 1.278 radians per second, which ends up being about 12.2 revolutions per minute. So about a third as quickly as a vinyl record player turns around if you're listening to an LP. So look at that. Hopefully that makes sense. The idea here is that if this computer rotates the ship around at that angular velocity, the centripetal acceleration at Frank's feet will be equal to regular acceleration here on Earth, 9.8 meters per second squared. Regular G here on Earth, 9.8 meters per second squared. So yeah, we've solved for omega. Now the second part is if we do this, what will be the artificial gravity at Frank's head, which is 2 meters closer to the axis? Well, if this ship has a radius of 6 meters and Frank's feet are 6 meters away from the axis, but his head is 2 meters closer, that means his head is going to be 4 meters away from the axis. So now we're going to plug this in. This time we know omega, and we just figured out that the radius is 4 meters, and we're solving for g. So if we do this, we're going to get a g at Frank's head of 6.53 meters per second squared. And again, at his feet, it's 9.8 meters per second squared. So this would be extremely disorienting if you were to actually do this. So if you were to stand there on this kind of spaceship, which has a radius of 6 meters, so pretty big as far as spaceships go, you would have regular gravity at your feet, but you would have much less gravity up here at your head. And this would mess you up physically and make you dizzy and probably vomit. And I don't think people could deal with this for very long. So the reason is, if you think of what your heart does, your heart pumps blood all throughout your body. It's got to pump blood up to your brain, and it's got to pump the blood from your feet back up to your heart. So normally when you're standing here on Earth, you have just G, 9.8 meters per second, all over the place. So your heart's got to do the same job all throughout your body. If you're on this spaceship and it's spinning like this, if your heart is pumping hard enough to get the blood out of your feet, where the gravity is 9.8 meters per second squared, it's going to be pumping way too hard to get the blood up to your head. So your head would kind of fill up with blood. It would feel like, that feeling if you're hanging upside down for a long time. I don't know what you do with your spare time, but if you hang upside down, that feeling of blood rushing to your head, it would feel like that, and it would be very uncomfortable, and I don't think people would be able to deal with this. The other thing that would be really weird is if you were just standing there on this rotating spaceship, maybe you could adjust to this after a while. But if you're standing there, you're standing upright, if you suddenly bend down to tie your shoes, the sense of gravity you're feeling at your head is going to change rapidly. Your head's going to feel much heavier as you start to bend down than when you're standing up. And that would be really, really weird. So, yeah, if the spaceship were this big, I think that would be too big a difference, and you wouldn't be able to deal with it, at least not for very long. So if you made the spaceship much bigger, so this would be a huge spaceship that had a 100-meter radius, then the difference between the distance from the axis to your feet and the axis to your head would only, would still be 2 meters. So the first distance would be 100 meters. The other one would be 98 meters. If you do the math, the same kind of thing applies. You would still have stronger gravity at your feet than you do at your head when you're standing on the floor of this much larger spaceship. But the difference wouldn't be as big, so you could probably deal with it. So if you made an enormous spaceship, so 100 meters in radius, so 200 meters in diameter, so this thing is huge. It's bigger than 2 football fields. You could probably deal with it. So, yeah. So I'm going to put a link to this video in here. This video is really fun. So this is how we train our pilots, both in the Air Force and in the Navy and the Marines. And yeah, quick trivia question. What country has the world's, let me rephrase this, what's the largest air force in the world? So, not a trick question if you think about it. You're probably not surprised that the United States Air Force is the largest air force in the world. What is the second largest air force in the world? The second largest air force in the world is the United States Navy. The Navy flies a lot of planes, and it turns out that the Navy has more planes and more pilots for those planes than the Air Force of any other country in the world. So, might get you to rethink the way we allocate our resources and our military spending. So, yeah, anyhow, this is how we train our pilots. This is at an Air Force base, so these are probably Air Force pilots. Maybe they train the naval guys here too. Guys and girls, there are female pilots in this video, you'll see. But basically what's going on here is this is a centrifuge. This is like the zero gravity ride, but taken to the nth degree, because this is how we train our pilots. Because our pilots, especially the fighter pilots, have to be able to make these rapid maneuvers, and they pull a lot of G's, is how you would say it. So here they're training these people to deal with what's called G-lock, G-force induced loss of consciousness, or gravity induced loss of consciousness. So what's going on here? So these guys, it's going to be hard to tell when you're actually watching the video, but the pilots are sitting in this kind of bulb place like here. I don't actually know which way they're facing in this thing, but they're in here, and this is a big centrifuge. It's going to spin this thing around. So these guys are going to go around rapidly. And meanwhile, you have their instructors up here, and they're watching this live, and they're watching these guys on camera. And they're testing these people to see how well they can handle this G-lock thing, or handle these G-forces. Hopefully they don't do G-lock, is how they would say. So yeah, I'll put a link to this video. When you're watching this, one thing is up here in the upper left, it tells you how many G's they're pulling. So when this thing is not spinning, it's just going to say G equals 1.00. They just have the regular gravity of the Earth pulling down on them. As this thing starts spinning around, they start to feel this centrifugal force, and this number is going to go up. So they do it two different ways. In the first part of the video, they do it gradual onset. So they put the pilots in here, and they just spin them around, and they get them up to speed, but kind of slowly. So you see how many G's they can handle that way. Then in the next part of the video, they do it with what's called rapid onset. So they spin them around, they're just going around kind of cruising, and then they rapidly spin this thing up, and the G-forces shoot way up. And you'll see how these guys deal with these sudden high G-forces. And turns out some of them deal with it better than others. So yeah, I'll put a link to there. Watch it. It's a fun video. It's a short video. You'll like it. So finally, back to 2001: A Space Odyssey. So here's how they actually did the shot, if any of you are interested in how they make movies. So one, this is what the spaceship is supposed to be in the fictional world of the spaceship. So here's how they actually filmed this shot and other shots. So they basically made a gigantic hamster wheel, essentially. So for some shots, like this one, what they do is they lock the camera in place, so it seems like the camera is not moving at all, and then they spin this giant hamster wheel. So as this thing goes around, the camera's moving, but because it's locked in place relative to the whole set, it seems like the camera's not moving. And as this guy, Frank, is running around, basically the wheel is spinning underneath him. This is what happens there. In other shots in this movie, they kind of follow the astronauts as they're walking through this. There's actually two giant rotating spaceships. They do it different ways. But in the other shot in this movie, maybe you can tell that this gap in the floor is a little bit wider. So if you can look at this picture here, essentially they have a camera, a giant camera stand with the operator and everything. And there's kind of a big fin that's sticking up through this gap in the floor, holding onto this. And then they spin the whole spaceship, they spin the whole set, and the fin just stays in place. And as the set spins underneath these guys just walk along the bottom of the hamster wheel, and you get the really neat effect. So, yeah, again, awesome, wonderful movie. Very deep ideas in this movie. People your age think that it is a slow movie, but people your age are wrong. This is actually a wonderful movie. Mr. Mencher loves it. So any of you literary artists or anyone taking the film studies class, yeah, he loves this movie. It's an awesome movie. Watch it on a big screen. Watch it in a dark room with good audio. If you love classical music, the most effective use of soundtrack in any movie in this one. It's just really, really beautiful. Yeah, great movie. And that's it for this part. So hopefully you guys found that interesting.